Okay, so today we're getting our hands dirty with A2 level physics paper 5. This is the one that really tests you on, actually applying the physics, not just remembering stuff. We've got excerpts from a level physics paper 5, planning, analysis, and evaluation to kind of guide us through it, written by Ayobami Peter Oluwafemi Bengbos.
And it's a different beast, this paper. It's like, you've got the knowledge, but can you prove you can use it in a real, experimental setting? That's what's so cool about it, I think.
Right, so less about just knowing the textbook and more about showing you can actually, do the experiment, yeah.
Totally. Think of it like knowing the rules of football versus actually getting on the pitch and scoring a goal. You know what I mean?
I love that analogy. All right, so let's break down the first big challenge, which is question 1, the experiment planning question. This feels like this is where the real physicists get separated from, well, everyone else.
Yeah, it's a tough one, for sure. And it all starts with defining the problem, right? Like, you're given this physics problem, this relationship you've got to figure out. The key, figuring out your variables, they're like the actors in your physics play, you know?
Okay, so setting the scene, figuring out who the characters are and how they interact. So we've got our independent variable, the one that we, the experimenters, are changing. Like, we're in control of that one.
Exactly. And then on the other side, we've got the dependent variable, the one that changes because of what we're doing, the one we measure to see if, our manipulations are actually having an effect, like cause and effect, but in the physics world, right?
Right, cause and effect, got it. So we've got our actors, now we need to direct them, right? That's where this methods of data collection section comes in. This feels very, hands-on, even though it's all on paper.
Absolutely. This is your game plan. How are you going to change that independent variable? How are you going to precisely measure the impact it has on the dependent variable? What equipment do you need? It all has to be crystal clear. No winging it here.
Right, and how do you make sure it's a fair test?
Exactly, controlling those other variables. Classic experimental design right there.
Right. Okay, so we've got our methods. Now we need to visualize it, right? Setup of the apparatus. Sounds like we need to get artistic.
A clear labeled diagram is your best friend here. It's like the blueprint for your whole experiment shows how everything's set up. And honestly, even if you don't explain it perfectly in words, a great diagram can save you. Shows you can visualize it. That's huge.
A picture's worth 1,000 words, as they say. Okay, on to the method of analysis. This is where we put on our data detective hats.
This is where your math skills come in, for sure. You might be given an equation, but the real skill is knowing how to make it work for you. The goal is always to get that equation into a linear form. Y equals mx plus c, remember that. Plot a graph, see the relationship nice and clearly.
So we need that straight line on the graph. Is it just for, aesthetics, to make our physics report look good?
No way. It's all about understanding what that relationship is between your variables. The slope of that line, the m, that tells us how much the dependent variable changes for every change in the independent one. And the y-intercept, the c, tells us the starting point.
So it gives us that visual representation, and then the slope and the y-intercept, those become tools for actually understanding the physics of what's going on. That's really cool. But before we get too excited about data, let's talk about safety. Every good physicist knows safety considerations are crucial, even if our experiment's just on paper right now.
Absolutely. Got to be responsible. So you're designing this experiment, right? What if? What if this happens? What are the potential dangers? Got to think about those.
Right, if you're using lasers, eye protection is a must. Or if you've got heavy objects, some kind of safety net or something to prevent accidents, being proactive.
Exactly. You're like a safety inspector now. Identify those risks with the equipment, the procedure, everything.
Like a risk assessment checklist running in your head as you're designing?
Exactly. Okay, so now, additional details. This is where you get to show off your knowledge.
Okay, time to impress.
Yeah, like you've laid the foundation, now you built the house. Show a deeper understanding. Can you predict what might cause errors and how to minimize them? Can you explain why you chose specific apparatus and how it all works in detail?
So going beyond the basic setup, showing you've really thought about the details that make a real-world experiment work.
Yeah. Like, let's say you're using a set square to align something. You could mention how that ensures a perfect 90-degree angle and why that's important for your experiment. Or, if you're using a ramp, explain that a spirit level ensures it's perfectly horizontal so nothing rolls off or gets skewed. Those little things.
Showing you're not just following instructions, but you get it. You know the why behind every decision. Okay, on to question 2. Data analysis and uncertainty.
This is where we get to play with some real data. Those numbers, they're the heart of any experiment.
And in the real world, those numbers are never perfect, are they? There's always some uncertainty, like you said.
Exactly. Question 2 is all about showing you can handle that. Take those real-world measurements and still get some good insights. Because, yeah, no measurement's perfect. It's like, you're a detective, got to find the clues in the mess.
So less about the right answer, more about understanding, like, the range of possibilities.
Yeah.
That uncertainty is just part of it.
You got it. And remember how we talked about getting that linear relationship? That comes back here.
You mean transforming our equation to that y equal mx plus c format?
That's the one. So, yeah, you've got your data, probably in a table, with those uncertainties.
Yeah.
And we want to plot it. Try to get that straight line.
Okay, so far so good. But the uncertainties, those have to go on the graph too, right?
For sure. And that's where error bars come in. Little visual cues to show, like, how much wiggle room we have around each point.
Yeah.
How confident are we in that measurement? Error bars tell us. And when we draw our best fit line, it's got to take those into account.
So it's not just about hitting the data points, but showing the overall trend while being honest about the uncertainty.
Exactly. Our graph is showing more than just the relationship. It shows how much we trust those measurements. And speaking of trust, got to calculate the gradient of that best fit line, right? So it's important. But even the gradient has uncertainty, and we can't forget that.
Right, because the line itself is just the best guess, based on data that already had uncertainties built in. So how do we figure out how uncertain our gradient is?
This is where worst fit lines come in. It's a cool trick, actually. Imagine drawing the steepest line and the shallowest line that still go through all our error bars.
So we're finding the extremes, basically, the range where the true gradient probably lies.
You got it. And the difference between those slopes, that gives us an idea of the error in our gradient. It's about being honest, showing that we know our measurements have limitations.
This makes me think about something you mentioned earlier about how experiments in the real world, they don't always go to plan. What happens when something unexpected messes with our perfect setup? How do we deal with that?
That's the art of experimentation, my friend. Adaptability. We've been talking about question 1, all that careful planning. Yep. But real life, research, it can be messy.
Yeah, I bet. So it's not enough to just follow a recipe. We have to be able to think on our feet, deal with surprises, and change our approach if we have to.
Exactly. Let's say you're doing that classic Hooke's Law experiment, right? Spring, weights, measuring extension. Sounds simple enough, yeah?
Physics 101. What could go wrong there?
Imagine this. You're halfway through, recording everything nicely, and suddenly the air conditioning kicks on. Now there's a draft blowing across your spring.
Oh, no, your measurements are all messed up.
Exactly. Now your spring's swaying, throwing off those precise readings. That, my friend, is a new variable.
So what's a physicist to do? Give up?
Never. This is where you adapt. You've got to recognize that draft as a new factor and find a way to deal with it. Maybe you shield the apparatus, or maybe you incorporate the draft into your analysis. Just acknowledge that it's there.
So being observant, spotting those hidden variables, and figuring out a way to neutralize them, or at least account for them.
Exactly. Or imagine you're working with a circuit and there's electromagnetic interference messing with your readings. A good physicist, they'd try repositioning things, maybe using some shielding, or even filtering the signal to get rid of the noise.
Like a detective, always looking for those subtle clues that something's interfering with the case.
Precisely. And sometimes it's not external stuff. Sometimes it's the equipment itself that's the problem. What if you're trying to measure the speed of something really fast, like a projectile?
Okay, like a bullet or something.
Sure, you might start with light gates and timers, but what if that bullet is too fast? The timer can't keep up.
So your original method is just not good enough anymore. What then?
Time for plan B. You've got to get creative. Maybe try high-speed video recording instead. Film the whole thing, slow it down later, and then you can track the projectile frame by frame.
It's amazing how a limitation can force us to think differently.